Hello and welcome back to Source Dive, where we spend time delving into some of the most interesting open source low-level code bases out there on the web. At the moment we're looking at XV6. This is the third episode in a series of us looking into the XV6 code base. And XV6 is basically an open source Unix-like operating system that is kind of designed and built for teaching purposes and learning purposes. So it's kind of the ideal playground to learn about some actual real kind of deep operating system concepts, but also not be completely overwhelmed with all of the special cases and the hardware restrictions and all of that kind of stuff that comes with kind of a real world operating system. So in the previous episode, we were actually examining spin locks. We looked mostly into the spin lock mechanism. So that's kind of a deep system level concurrency primitive, and that is used all over the operating system in order to make sure that multiple CPUs trying to access certain kinds of resources are forced to kind of take turns and not sort of clobber each other as they try to kind of control a resource, which may be memory or it may be kind of access to a hardware peripheral, it could be anything. Okay, and sort of where we were with that was that we were looking into this console init function. So this is kind of the main function that happens once all of the kind of boot level architecture specific stuff has occurred. We end up here, and this is kind of the operating system properly booting. And we only do this pathway in the code if we are CPU 0, i.e. we're the core, like the first core. We can have multiple cores. The rest of the cores kind of spin around waiting until this main part is done. But yeah, basically we were in this console init function and we looked into the inner lock. That's kind of where we left off. What I want to do today is to really get to the point where we understand how Printf is actually working on this system, the kernel Printf. So basically, you know, when we print a message like this out to the screen, what's actually happening under the hood? Like, how does that relate to low-level hardware? Like, how are we talking to the like whatever we're using for a console in that way? How do we get, well, in this case, output, but also how does it get input? And the next level up from that I also want to cover today is like, how does printf itself work as a function? So you may have never ever thought about this before, even if you've written a whole bunch of C. Normally, you don't implement printf yourself. That's just not something that people do. And I think even if you're working on an embedded system, normally the way it's done is that you sort of mock a bunch of Unix-like or POSIX system calls, and if you kind of implement the right set of system calls, then the standard library underneath is able to give you printf based on that. So like, we're going to look at how printf actually works. Like, how do the format strings work? How does it work as a Variadic function? So if we get to where I want to be today, we're going to kind of cover everything here, and in the next episode we'll be able to look at the kernel physical page allocator, which is like a proper, you know, actual real kernel level thing that's going on, and it's really beautiful. So stay tuned for that. But today let's look into the console and printf. So as we come into this console init function, the next call that is made is one to UART init. And UART, and I think I discussed this briefly in the previous episode, but UART is basically just a physical communications kind of protocol standard, physical layer description, all of that. So basically in UART you have two wires, essentially. You have a receive wire and a transmit wire, and you have to think about those wires are labeled in accordance with like who is doing the receiving and the transmitting. So you always need to be conscious of like how you label those. But yeah, basically you can send and receive on two wires at the same time. So there's kind of this full duplex communication that's going on. You don't communicate over one wire and therefore have to kind of alternate between receiving and transmitting. You can receive and transmit at the same time. And Yeah, so this actually we'll take a look into this in a second, but I will draw attention to this for a second. I think we also mentioned this briefly, but just to wrap it up in this console episode, the console is kind of an abstraction over the physical hardware. So the idea here is that we could have a console running on different kind of underlying hardware definitions. The console itself is just something that you can read and write, and the idea is that it's displaying stuff and taking input. That's it. That's the console's job. So that kind of gets abstracted away into this idea of a device. Now, if we go and look at this struct here, it actually lives in file.h. This description of this struct. So it's a major device number to device functions. This is not actually strictly describing what's going on here, but basically in this type of struct, you can have a read function, you can have a write function. And then there is somewhere described this array of devices. So that's in file.c. And you may have heard this expression that in Unix everything is a file. Well, this is the idea here. This is what is kind of meant by that, actually, is that we can treat physical devices and slightly abstract devices like a console. We can treat them like a file. So a file, you can open it, you can read from it, you can write to it. Sometimes you can seek through it. And so those are kind of like sort of generic operations. And yes, they apply to files, but they can also apply to many other kinds of devices. And it turns out that abstraction, with some glue, can get you really far in how you represent things. And having a uniform interface between kind of like how you talk to files and how you talk to devices turns out to be really useful. So that's kind of it. We're not going to go into the whole file mechanism here, but basically there is a list of devices that have read and write functions. In xv6, you can only do read and write. You can't do more complex operations. But yeah, we've got that, and console is one of them. So if we go here to this define, you'll see that the console is defined as 1. So the sort of at index 1 inside this device list, we're assigning our console's write and read functions here, so that when we try to read and write from the console, we'll end up calling into these functions. Okay, let's figure out how UART works, because that's actually sort of the core here. So we've got this UART function, UART init, and it's quite well commented. It's quite obvious what it's doing if you read the comments, but we're going to go deep into how this works. So I'm just going to first scroll up to the top of this file, and we can see that it says that this is a low-level driver routines for 16550A UART. What is 16550A UART, you might ask? Well, it is essentially a certain kind of chip. There's a chip out there called the 16550. I think there are various, it's a family of chips, so there are various different ones that you can have there. And it is a UART chip that's quite old at this point, and I think it was even sort of an evolution of some earlier UART chips. It is a design that is meant to be memory mapped. It has a set of registers that you use to kind of set it up and control it. And that kind of interface of how those registers are memory mapped and how you communicate them, what all the bits mean inside, that interface turns out to be quite simple, for one. But it's also just like being quite widely adopted. So it's a quite standard interface. And the nice thing about that is that if you write a driver, and this is what this code is, it's a driver. So it's something that is kind of bridging the high-level code with the low-level code. If you can write a driver that talks to like a common interface, so that works across multiple chips, well, that's great, right? Because you don't need to write multiple drivers. Now you've got one driver that is able to talk to multiple low-level systems, even if they're different, even if they have different performance characteristics, or maybe they have different restrictions. If you've got this like fundamental layer that's common, it's really great. You've got a common driver. So that's what we're going to be kind of studying today. And of course, you have to map all of this into the idea that this xv6 code is designed for a virtual computer. So it's designed for the virtual QEMU computer. And that has some interesting implications. Well, what that actually means when I say that is that QEMU, it's just an emulator, right? And it can emulate multiple different kinds of chips and multiple kinds of different systems. But when it does emulate a system like this one, when we're talking about emulating a risc-v 64-bit system, what you actually get is a computer that has some sort of virtual hardware associated with it. So one of the things is that it has a virtual 16550A chip. And if we actually just sort of go to this definition, I happen to know this, it would you would look around the files to figure this out. This actually brings us to a file called memlayout.h, and this is the physical memory layout of the machine, the QEMU virtual machine. So what we can see here is that various addresses map to various pieces of kind of virtual hardware, and of course RAM is also virtual hardware, but we've got other kinds of hardware as well. So if we look here, the first 1000 hex, from 1000 hex on, that's the boot ROM. So that is basically the really low level kind of system code that runs from a ROM when the machine powers on, so the virtual machine powers on. We don't have access to this code, or rather it's not part of our code. Normally you wouldn't have access to a computer's boot ROM. It's kind of like a manufacturer specific thing. But in this case, yeah, there's a boot ROM there. From this address we have the clint. We talked about that in a previous episode. That's the core local interrupter. It's basically a piece of hardware that's dealing with managing interrupts in the system. Here we have the plic. That's another piece of virtual hardware. We'll get into that at some other point. And here at address 10 million, we have, that is 10 million or 1 million, it doesn't matter. In any case, at hex address million here, we have the virtual UART. So this is the base address of the UART, and sort of at various addresses within this space, we'll be able to write to certain registers on that virtual chip. And then there is the virtual disk, which is the hard disk, and there's a whole bunch of extra stuff going on here. This is where RAM is, where the machine is, where it boots up. Okay, so what we can see here is that this UART define, this UART0 define, is just a number, and it just refers to this address basically, but it is just a number in this system, and everything else here is also just a number. Okay, so let's go back to that init function and let's have a look at what it's doing. So the first thing we can see is that there's a comment that says disable interrupts, and then it's calling this function here, write-reg. The first argument is IER, which is a define of just the number 1, but it's labeled here in the comment, and if I scroll up here you can see where that comment comes from. It's up here. It's labeled as the interrupt enable register. So we're writing 0 to it, so we're disabling interrupts. I want to point out here that all of these functions here with write-reg, they're not talking about the system as a whole, they're talking about the UART chip. So when we talk about disabling interrupts, we're not talking about disabling system interrupts. We're talking about disabling the interrupts that this chip would put out into the world. Just to make that clear, because it can be confusing. So what does this write-reg thing do? Let's go to that. It's not actually a function, it's a macro. And it's a macro that takes in this reg, which is some sort of address fundamentally. Or sorry, it's one of those, one of these defines here. So it's just like 0 or 1 or 2, 3, 5. Like it's just one of these kind of numbers that are defined up here. And then the v is some value that we're saying. And what you can see is that there is a pointer dereference happening. And we're doing something with a reg function here that we're using to like translate this register number we've passed in into a memory address. Then we are dereferencing it, and then we're able to assign this value into it. So we're able to write to memory this way, or memory mapped IO this way. So what's the reg function doing? It's another define, it's another macro. And what this one is doing is literally just taking the base UART address that we just looked at, adding the register number here. So in this case, the IER is 1. So we'd be looking at register 1,000,001 hex. And then this part is just casting that number into a pointer. So it's saying this isn't just a number, this is a pointer to a memory address. And specifically, we end up casting it to an unsigned char, an unsigned char pointer, which just means a byte, basically, a pointer to a byte. So not like a pointer to a uint32, which would be 4 bytes in a row. No, this is just a single byte, so we don't have any alignment troubles. And we're also using the volatile keyword as well. And I think the volatile keyword can be kind of scary if you are not from the embedded world. But let's just take a quick look at why that's used. So we have this thing, right? And what's happening fundamentally here, now we know, is that we're writing to a memory address that represents a register inside a piece of virtual hardware. So not memory, it's a piece of virtual hardware. And we are writing a configuration value to it, essentially. So if we were to have something like this, where we did the same thing twice, in a compiler, in a regular old compiler, if all the compiler sees is that we're writing to some memory address with some value, that's all the compiler sees. So it sees 2 of those happen in a row, writing to the same memory address with the same value. And any compiler that's smart enough is going to look at that operation and go, you know what? I don't need to do that write twice. I can do that once. So it will just eliminate the second write. But that's not what you want when you have memory mapped I/O, because writing the same value a second time to a configuration register might have some side effect, right? It might do something that isn't the same as just writing to memory. It's not just recording a value. We're actually configuring hardware here. So that is the reason we need to mark this as volatile. Volatile is a keyword that essentially just means compiler, don't do anything here. Don't try and get smart. Don't try and perform optimizations. This is something that could have side effects. Therefore, just leave it alone. Just let it be. So yeah, you don't want to use volatile unnecessarily. You want to let the compiler do its job most of the time. But in this case, when we're dealing especially with memory mapped I/O, that is the time that you want to use volatile. Okay, so now we've kind of understood the mechanism that's at work here, and it's kind of the same mechanism, or in fact it's exactly the same mechanism that's used in the clint that we looked at previous episodes. Now we can just look at the rest of what's happening here. So we're going to go into a special mode to set the baud rate. So sometimes when you write a special value to a special register, it will change its normal behavior and it will do something else. So this is just one case of that. We write to this LCR, the line control register. That's at offset 3, which means we write to address 1,000,003 in the terms of the physical address. And then we write this value, so a 1 bit shifted up by 7. In the case of this chip, what that means is that we're going to set the baud rate. So it means that the next 2 things that we write to just address 0 and address 1, so offset 0, offset 1, they actually have a special meaning, and it means that we're recording a baud rate. And this is because we need to write a value that's more than 1 byte. So this is why we kind of need some special signal that we're going to do something like this. But basically, these 3 writes together are one piece of configuration. If you don't know what the baud rate is, by the way, UART is a protocol where basically you're wiggling these electrical lines up and down, and kind of the wiggles denote, if they're high or low, they denote like 0s and 1s, and that's how we're transferring data, basically. But usually when you do that, you have a clock signal associated with your wiggling data line. So what you can see is that when the clock goes high or when the clock goes low, that will signal that data is like in a certain state. So that is going to let you like kind of pull out like the good values. Like this is a 0, and I know it's a 0 because the clock went high at this point. So then I can pull the 0 out. UART doesn't have the clock, so there's no clock to reference. Instead, both sides of the channel, they agree upon a fixed time scale. And that's called the baud rate. So that's the number of bits that are occurring per second. So what happens is on any of those lines, we'll see it go from what's called the idle state. We'll see it drop into kind of a start state, like an indication that basically a transaction is about to begin. And from that moment, both the side that's receiving data starts a counter. And it's counting in proportion to how long it's basically counting to figure out when to sample the bit, because there's no clock. So it needs to do that according to the agreed upon data rate. So that is why we need to set a specific baud rate in these cases. In this case, it's just 38.4K bits per second. Okay, so then after those three writes have been done, then we are kind of leaving the set baud rate mode, and we are going to set the word length to 8 bits, no parity. What that means is that as we make transfers on the UART, we can transfer a different number of bits per transaction, or it's one time configured, presumably. So a sensible value here is 8, right? You want to transfer 1 byte at a time, but you can transfer 9 bits at a time. You can transfer 7 bits at a time. There are reasons that you may want to do this. There are legacy reasons that this may be the case with certain devices, but in most cases, I think transferring 8 bits is going to be the thing that makes sense, and it's what you're going to see the most often if you look at UART. Okay, then we're going to reset and enable FIFOs. This is basically an internal piece of memory to the UART chip. A FIFO is a first in, first out queue. It's basically a memory structure where you can place items into it, and when you come to retrieve those items later, because you're buffering them essentially, when you come to retrieve them later, you get them in like the order that you place them in. So the first thing that goes in is the first thing that comes out. So what's happening here is we're basically making sure that those FIFOs, whatever state they were in, now they're empty, and we're enabling their use. So basically, as data starts to flow into this chip, or flow out, if we ask data to be sent out, they're going to go into these FIFOs so that we can kind of queue them up and send out, multiple bytes. Now, of course, one thing to remember here is just as a side note is that FIFOs, like anything else, they have a limited amount of memory. So there's a limited depth associated with this FIFO. So let's say you can push, I don't know what the actual number is here, but let's say you can push 16 bytes at a time into a FIFO. If you try to push one more byte into the FIFO after that, things don't make sense anymore, right? You've the box was full and you tried to put more stuff into it, so it's not going to work. Probably you get some kind of error condition, but you just know that at that point things are breaking down. Okay, finally, the last thing that is done is that we enable transmit and receive interrupts. So basically, these are interrupts that are delivered by the chip itself to the computer. So whenever a transfer is complete, whenever we send 1 byte out of the UART, an interrupt is given to the computer. And whenever we receive a byte, an interrupt is also given. So this is useful because, especially when you're transferring data, if you didn't get an interrupt when the transfer was complete, because it's not instantaneous, it does take time. Remember, right, we were going at 38.4 kilobits per second. Well, that means that we're like, if you tried to send a whole bunch of data, there's a time that's going to take. It's not instantaneous. And therefore, if you wanted to know when you could transmit your next byte, you'd have to spin until your previous byte was done. You'd have to sort of keep checking continuously, reading from somewhere, like a register. Am I done? Has the byte been sent out? Has the byte been sent out? And if it's not been sent out, you kind of need to spin around and wait there. Whereas if you get an interrupt that tells you, transfer is complete, you can send another one, well, what you can do is you can actually and you're running on a multi-process system, you might try to send a byte out, and then realize like, wait, no, it's full, I can't send it, so I'm going to have to wait around, then you can just put that process to sleep and you can switch and do something else that's useful. So there's a big difference between waiting around and not being able to do any other useful work, i.e. being in a while loop, and the like letting the operating system kind of manage who can do useful work at a time. So that is why the interrupts are actually really useful. Okay, and finally what happens is that there is a spin lock setup that's associated with the UART. So of course, just like anything else in the system, the UART also has a spin lock associated with it, and that means that only one CPU can be sort of telling the UART to do something at a given time. So yeah, that's pretty much the setup. And if we go back here, if we go to the console, we can see that like after setting these up, we write into these console read, console write. That's the end of that function. So then there is the printf init. So let's have a quick look in there in the printf init. So that brings us into a file called printf.c. And all that happens in this file, or in this function rather, is that we init a spin lock for the printf. So printf has a spin lock too. And then we end up setting this locking variable to 1, to true basically. And if we kind of go up to this structure up here, this PR structure, the print structure presumably, again terrible names, what it actually contains is a spin lock and this Boolean value locking. And what we will see at some stage when we go further into this is that the locking here is referring to the fact that when we use printf, it is or is not going to use the spin lock. So there are specific reasons why in some circumstances you might not want to use the spin lock. But yeah, so actually you can see that immediately after that we're able to start using printf, which is kind of wild in a way. Like it seems that we haven't really set up enough stuff, but all of a sudden we're able to print. So I think the next big thing for us to look at is, how does printf work? What happens when we try to do printf? And I think this is really interesting. I think this is like, I was really fascinated when I read this code, and I think I'm really excited to share kind of the inner workings with you. So let's go into that one. It's also in the printfc file. And the comment here says, print to the console, only understands %d, %x, %p, and %s. So if you've used printf and you've used C before, then you probably know what those roughly mean, or you at least understand what that's getting at. If you haven't, then allow me to just give you an example of where these kind of things are used. If we scroll down here to the other CPUs, when they're eventually, all the setup has happened, the other CPUs can print something to the screen. And in this case, it's printing %d starting. And then there's another argument to printf here. So like you can see in one case we only provide one argument, this string. In this case we're providing 2 arguments. And this is the CPU ID. So basically this is saying like heart4 started, heart5 started. And somehow printf is able to kind of take this dynamic value that comes here and insert it into the string to be able to be printed to the screen. So that's kind of what's going on here. That's what's going on in this printf. And there are 4 different things that it says that it supports. So it supports %d. This is just printing an integer to the screen, right? Just a decimal integer. There's %x, which is printing a hexadecimal integer to the screen. There is %p, and that's when we print a pointer value to the screen. And finally there's %s, and that's when we print another string. So there's kind of like this embedded string inside the string that you're trying to print. So that can be useful if you've got like the name of something somewhere stored and you want to print like this thing named %s did this thing. So yeah, those are kind of like the things you can pass to printf. So now we know that, let's kind of go into this code and it goes from here, from line 70, where does it go? Line 63 down to line 116. So, it's not an insignificant function. But we're going to walk through it step by step, and you will understand it after this, or at least most of it, the important stuff. So, first interesting thing is that printf is a variadic function, and that means that it takes optional number of arguments, right? It doesn't have a fixed number of arguments, and by kind of just by necessity, in a way, when it does have some extra number of arguments, the types of those arguments are not well defined. So it's not that we passed in a, what was it down here, CPU ID is returning an int, but we could equally put a string there, right? Or we could equally put a a floating point number if this was supported. But that's not known. That's not known to printf. So all that's known is that printf takes this string called format and then some optional number of arguments. So how does that work? That's kind of interesting and tricky. I think that this is not something that even people that program in C day to day typically use that much. Unless you're a library author, you might want to use it there. But in most cases, like Variadic arguments pretty much agreed upon to be not the best design principle. But in some cases, like in printf, there are very few ways that you could do this otherwise. So, okay. So how does this work? Well, it turns out that in C, there is kind of a standard, this is a standard thing, right? The fact that there is this ... that signifies that multiple arguments are possible here, that is kind of built into C as the language. And in the standard library, if we go up to the top here, there is a header file called standardarg. And this basically contains like all the stuff that's required to basically process the variadic arguments, the unknown number of variadic arguments. So in the beginning here, there's something called a VA list, a variadic argument list. And they call that the AP, presumably argument pointer. Who knows though, because it's just a 2-letter name. And then we have a couple of variables here. We have an I variable, we have a C variable, and we have locking. Then there is a sort of arbitrary string pointer. There's no value associated with it. These are just uninitialized values here. They're just things that will be used in this function. So first of all, what happens is this locking value is set to whatever PR locking is. So remember I talked about the fact that this is used to check whether we're actually going to use the spin lock mechanism. So this is checked. If locking, acquire the spin lock. Now, immediately after that, we check to see if we have a valid format string, because strings in C are just pointers to an array of characters, like an unknown size array of characters. And the way that we know the string ends is that it ends in a 0 byte. So it's called a null terminated string. So if like the thing that gets passed in here, the string, is actually a null pointer, then we're going to do something called panic. And panic is where we just basically sort of crashing the system with a certain message. We print it to the screen, and that's it. And it's kind of funny here because we're in the printf function, but we're somehow going to print something to the screen. So let's go into this panic function. We'll see that panic is also in the printf.c file. And what it does is it sets the locking variable to false. So we're no longer using the lock mechanism. And then we call printf with panic, then with the string that is the message, the error message, and then with a new line. And then finally, we set this this global variable here, panicked, to true. And the idea here, as it says in the comment, is to freeze UART output from other CPUs. And then we go into an infinite loop forever. So we sort of will crash here, basically. That's it. That's how that works. Like, that's how panic works. So this panicked variable is going to be looked at by a few places. But what you can see is that here, if we try to acquire a spin lock, but then the format string was not valid, well, we would panic, so that would mean we would turn off locking, and then we would actually come back here and we would print this null format message. We would come all the way through the function again, but because we weren't locking, we wouldn't try to acquire the spin lock, and then we would progress through the rest of the function, which we're going to look at now. Okay, so the first thing of interest is this VA start function. So this is there are a bunch of functions from this standard argument header that are used in order to actually process these variadic arguments. So what VA start is basically doing is it's setting up the fact that the argument pointer is going to start after this known argument format. And if we hover over this, you can see it's actually a define, and it shells out to something called the built-in VA start. And the interesting thing there is that that means that this is a built-in to the compiler, but it's going to be architecture dependent. So it's going to depend on whether we're on x86 or risc-v or ARM, how this actually works under the hood. So there could be many different ways. And that's why I'm not actually talking about like the specifics in memory of how this works, because it can change between different architectures. But basically, we're telling the argument pointer here like where it's going to start looking for variadic arguments, essentially after this format argument. So whatever that means to the architecture. Then we enter a for loop where we start I at 0, and not looking at the I variable here, but while assigning this value of whatever is at the format string at character I. Remember, format string is the string we pass into printf. Whatever is there, ANDed with ff, so make it into a byte, because C is actually an int, so it's a bit confusing type-wise. But what we're doing here is we're assigning this value into C, and when you do an assignment in C, it actually evaluates to a value, right? So it like an assignment has a value, and the value is just what you assigned here. So while this is not 0, i.e. we didn't reach the end of the string, because it's a null terminated string, so we didn't reach the end of it, we're going to do this loop, and then we're just going to increment I. So we're going character by character through this string, and there is just this tiny little optimization that is used for some reason, which is to assign C at this point. It does save a bit on the code, but I think also the compiler would probably figure that out. So I'm in two minds as to whether this kind of thing is really useful in the end. But, you know, maybe they tested that and it was. You know, you can always generate the assembly, look at what happens. We're not going to do that now. Okay, so what do we do, right? We're going character by character through this string. And what we do is we check, like, is the character that we got, is it not the percentage symbol? If it's anything else but the percentage symbol, we're going to call this function, cons put C. So that is the console put character. So put a character out to the screen. And if we go to that definition, that is of course in console.c. And the comment here says send one character to the UART. This is called by printf and to echo input characters, but not from write. So it's a bit tricky because what it's basically saying to us is that this function is going to be called in multiple places. So this is one of the places it's called, printf. But there are also places where it's not called. And in that case, obviously something else is done. So we'll look into that eventually. But for now, let's focus on this kernel printf example. So what we do is we check, is the character that we got equal to this special value of backspace? And you'll notice here that backspace is actually not a byte. This is like the first value outside of a byte. So this is not a 8-bit number. This is a 9-bit number at least. So if it's somehow equal to this special value, then that somehow translates to the idea of the user typing a backspace. And if that happens, then we're going to overwrite whatever is kind of at the whatever was like previously like behind the last printed character, we're going to overwrite it with a space. So what you can see is that there is a function called UART put C sync, and it sends this \b. So that's kind of a special character that refers to moving the cursor backwards. Then they print the same function is sent with a space, so that's presumably printing a space, and then we actually go back one step again. So every time you print something, you move forward a step, except in the case with this b, of course, because that moves back a step. But what's happened is we move back a step, we print something, that moves us forward, but then we move back again. And the idea there, of course, and this is confusing, I do understand, it's just to paint a complete picture here. We end up kind of back on the character so that we would overwrite that space with whatever we typed next. If it's not a backspace, then we end up just basically printing this character using this UART putc sync function. So that's the next thing. Let's go into this. That brings us back into the UART file. What I really love about this is that you see the abstraction stack that's going on. Printf is higher up in this abstraction, and then we end up dipping down into the next thing that's low level, like the lower level, which is the console. And then we end up dipping down one more level into the concrete hardware-specific thing, which is the UART. So this is kind of how you layer up a complex system. You actually don't just access the lowest levels at every point. You try to, as you move up through the system, kind of create more and more abstract interfaces. Of course, there's a cost associated with that, so you can't do that forever. Okay, so this is an alternate version of UART putc that doesn't use interrupts for use by kernel printf and to echo characters. It spins waiting for the UART's output register to be empty. So this is actually telling us, kind of getting at this thing that I talked about earlier, which is that when you transfer bytes, you don't want to spin and wait forever. Except for when you're in the kernel and you are kind of doing low-level kernel printing. In that case, you do want to spin forever because you don't want to switch from your kernel context into some other context. We will get into the idea of being in the kernel context and being in a user space context at some stage too. Kind of the idea of these different threads that are running. But for now, you need to just imagine that we are running in the kernel, right? We're not running user programs here. So the idea is we can't wait for an interrupt because we can't do anything else in the meantime anyway. We have to stay in the kernel. Okay, so what happens here is that we use this function push off and pop off. These are functions that are used to manage the interrupt stack. And they're used by the spinlock system as well. So if you didn't see the spinlock episode, it's probably worth taking a look at that to understand this mechanism. It's really interesting. Basically, we're tapping into that same thing. So we're just making sure that while we're in this function, interrupts are definitely off. And if we're the last function that was kind of asking for interrupts to be off, then it will turn them back on if they were previously on. So we get rid of interrupts, we turn them off. If we've panicked, we just spin here forever. That's going to have the effect of making sure that this core does nothing else because we've turned interrupts off. So there's no way to be interrupted to do something else. And we're going to wait for this register, the transmit holding empty, to be set in the LSR, the line status register. And the way that that works is we read the line status register using this read reg, and that basically does the same thing as write reg, but in reverse. So we're going to read that register, then we're going to mask off the bit that represents the transmit idle. So transmit is is it idle? Are we able to transmit? And while we read that and that bit is not true, basically while transmit is not idle, we're transmitting something, we're just going to spin in a while loop. And as soon as that becomes true, like we are idle, then we go and write to the register that is the transmit holding register. And that is where we put our output bytes. So every time we write to the transmit holding register, we're trying to ship out a byte from the UART. And we're writing out the byte, the integer here, the C, that we've put in there. So then we pop off, so we get off the interrupt stack and do all that kind of stuff that's to do with restarting interrupts if they were enabled before, if we're the last one. So that's it. That's how we print a character to the screen in this low-level driver, right? This is the driver-specific code for printing something to the screen. What we do is we end up just writing to one of the hardware registers on the chip, and the chip takes care of the rest, right? The hardware in the chip takes care of that for us. Like, we just need to make sure we adhere to its rules, like not trying to transmit something when it's not in its idle state. Okay, so knowing that, let's actually close up the UART. Now we understand this cons put C, the console put character. Let's close that. So what's happened here in printf is, if the character was not a percentage symbol, we print that character to the screen. Then we continue, so we end up going back to the next iteration of this for loop, where we would grab the next character and we would look at that. So let's imagine for a second that we did encounter a indeed encounter a percent symbol. So we've printed in this case up until here, and we've got to this %d symbol, or rather the percentage symbol. So what happens then? Okay, well, it's a percentage symbol, so we come down to this line, and what we're doing is we're assigning to the next character in the stream. So we're getting the next format character using this pre-increment operator on I. So we're moving the pointer forward, and we are grabbing the next character in the string. If that character is 0, then we're done, right? If that was like the null termination in this string, as in like there was the string looked like this, for instance, then we're done. It would actually be quite like a kind of error condition for that to be. It's kind of an invalid format string, but what else can you do but just like leave the break context? Otherwise, we're going to look at the next character. So we're now looking at this character. If it was D, then we're going to run this printf that uses another variadic argument function. If it's X, then we're going to do the same thing. We're going to like call this printf with a variadic, and maybe like there's one difference here. If it's P, then we're going to call into a function called print pointer. And if it's S, then we're going to run a bit of logic code here that prints out a string to the screen. There is one more case that's kind of valid, which is that there are 2 percentage symbols in a row, and this is for the case that you actually do want to print a percentage symbol. So in that case, you just print a percentage symbol. If you see 2 in a row, you print one of them. Finally, if there's anything else, as in something that isn't supported here, like %f, for instance, printing a floating point number, then we would just print percent and then that thing, so %f in this case. And that's just for debugging, so that the user sees like, oh wait, I can't use this print symbol, right? We're not going to create an error state from that. We're just going to print the thing and we'll use it like that. So we're going to look into these functions in a second, but let's just finish the logic here. So we go through every character this way, up to and including new lines and everything. We go through all the characters, exercising this logic. If it's not a percentage symbol, just print whatever it is to the screen. Otherwise, do one of these specific things. At the end, we call this function va_end, so variadic argument end, with our argument pointer, and that's kind of just wrapping that up, like kind of saying that we're done with this. We don't need to accumulate more arguments. Maybe we can free any memory that might have been associated with that. That's going to be implementation specific. And finally, if we were using our locking mechanism, we're going to release the lock, because we're done now. So we're going to release that lock back into the world. That's it. That's how printf works. So let's go into the specifics of this, because the specifics are really beautiful. So printf. So there are a couple of arguments that go into this. The first is this XX. Terrible name, but it's basically, this is just the number that you're trying to print, the value you're trying to print. The second argument is the base. So this is like the base of the number. Is it base 10? Is it a decimal number? Is it base 16? Is it a hexadecimal number? And finally, there is just an argument called sign. It's not immediately obvious, but this argument sign is actually it's saying, are we are we interested in potentially signed numbers here? So that's actually the question this sign value is looking at. Let's go through the logic, because it's quite interesting how this works. All right, so first of all, there is a buffer of 16 characters. So there's just like some memory is set aside, 16 characters. Nothing is in there right now. It's uninitialized. We've got a variable I and we have a variable unsigned integer x. So that's an int I, all of these are ints, but then we have an unsigned integer x. So what we do is we say if the sign, so did we say that we're interested in potentially signed numbers? If we did, and if then reassigning this value sign to the idea of x being less than 0, so is x a negative number? That's the question that's being asked here. Now the value sign variable is going to hold that value. Is x a negative number? If yes, then set x, or this x, right? So we're looking at xx. Very bad names, if you ask me. I think I've been clear about the bad names at this point. All right, so we set x to negative xx. So let's just think about what that means for a second. If we passed in -5, -5 here, and we said we were interested in negative numbers, is this value -5 less than 0? Yes, it is. So we set sign to 1, and then we set x to be -5, or 5. So what we're doing is we are recording the fact that it was negative, and we're setting it back to a positive number. So that's what this logic is doing. It's a bit confusing. I was a bit like, I really had to think about this the first time I came through this code. Otherwise, we simply assign whatever was in xx, we assign it to x. Now, there's one thing to note here, and that is that xx is an integer, a signed integer. So that means it can potentially hold negative and positive numbers. X is an unsigned integer. It can only hold positive numbers and 0. So what's going to happen here is that if xx did contain the value -1 and we weren't interested in the sign, that's going to just become like the value ff forever, right? Because that is the representation of -1 in unsigned form, 2's complement form. So we would end up printing like the highest integer value at that point. So just so you understand what's going on there. Okay, so at this point we've converted our number to a positive integer, and we have understood whether if it was signed, if we were interested in the sign, if it was negative at that point. So what do we do here? Now we loop through using a do while loop. We loop through a bunch of stuff in this buffer, and we end up filling up the buffer using this digits. And where is this digits? Well, it's actually defined just above here, and it is just an array of characters, a string actually, which contains the characters 0 to 9 and then A to F. So the numbers 0 to 15 in hexadecimal essentially. So this is a tricky bit of code. Like, you have to think about this a little bit. And in fact, I think it's good to, let's simulate it. So let's simulate a run through this function, and we will use the help of a terminal down here, just running Python in order to kind of look at what's happening. So, and I'm going to put this here so that you can definitely see it. Okay, so let's imagine that we passed to this function, we tried to print out, we did something like this, printf %d, and we had a value in x, and it's 1, 2, 3, 4. So we passed in, this was our thing. So basically we just want to print this value to the screen. No other values. Okay, so we're going to end up in this function, and we're going to have called this function with 1, 2, 3, 4, base 10, because it's a %d, and the sign well, yeah, in what you'll see is that the sign is always set to 1 in this thing. So yeah, so basically we're going to end up with this. And what's going to happen is we're going to come down to this part. We're going to say, are we interested in the sign? Yes, we're interested in the sign. Is 1, 2, 3, 4 less than 0? Well, it's not less than 0, so we're not going to do this part. We're just going to say that x equals 1, 2, 3, 4. So now this value x, not this one, I shouldn't have called this x. So now x is 1, 2, 3, 4. xx was also 1, 2, 3, 4. Okay, so then we have this buffer, right? And we're going to try and fill up this buffer with stuff. So at the moment it's kind of empty. But what are we doing? So we start at 0, and we're going to say that the first character in this buffer, 0, is going to equal digits, and we're going to index this digits array by x, this value x, modulo our base. So that's the base 10. So we've got these digits, and we're going to pick a character out of this using this as our index. Okay, so what does that look like? If we type 1, 2, 3, 4 modulo 10, that gives us the number 4, right? Basically, we're just dividing this and seeing what we would get as our remainder. So we're dividing by 10, and like whatever our remainder is, that's what we get back here. So in this case, it's 4. So we would end up putting using 4 to index into this digits. And of course, like basically what this does is it converts a number into its string representation of a number, right? That's the kind of the beautiful thing that's happening here. This is not the only way to do this, by the way, but this is what it's doing. So what we would have now is the number 4 at index 0 in this buffer. And then it's a do while loop, so we always do this logic once, and then we drop down and we evaluate the condition. And now what we're going to do is we're going to say that we're going to take x and divide it by the base and reassign it to x. And while that did not come out as 0, we're going to continue. So what does that mean? So now we have 1, 2, 3, 4. We're going to do 1, 2, 3, 4 divided by 10. And this division is a integer division, right? We're not like, if we did 1, 2, 3, 4 divided by 10, you can see that in Python we get a floating point number here. But we're actually dividing this using integer division. So we use 2 slashes here in Python. That gives us 1, 2, 3. So basically we're setting x now to 1, 2, 3. And 1, 2, 3 is not equal to 0, so we're going to continue again. So the next thing is going to be our value x, 1, 2, 3, modulo the base, which of course is not 3. It's going to come out to be 3. So 1, 2, 3 modulo 10 is 3. So then we end up putting that in here. We do this whole thing again where we do 1, 2, 3 divided by 10. Of course, this gives us 1, 2. We run the logic again, 1, 2 modulo 10. That gives us 2. So what you can see here is that we are like basically inserting the number backwards into this buffer. So we're like iterating through those digits backwards and building up the buffer. So in the end, what we do is we'll have this in the end when we're done with it. And of course, in the end, we're going to do 1 divided by 10, which is going to return 0. And so at that point, we'll break out of this loop. So we've been recording this value I, we keep that. And if the sign, like if this was a signed number, if this was a negative number, then we would add one more entry to the buffer, which would be a minus symbol, like this. So of course this wasn't a negative number, but if it was, like remember we just convert it back to its positive number, and then at the end we would just tag back on this minus symbol at the end. Really clever stuff if you ask me, because what happens at the end here is that we just iterate backwards using I, and we print out character by character. So we would end up printing this character, then this one, then this one, then this one, and then this one. Of course, what that's going to print is minus 1, 2, 3, 4, if we have minus. And otherwise, it's just going to print 1, 2, 3, 4. So that is how printf works for decimal integers. It's crazy. I think it's such a clever algorithm. Again, it's not the only way to do this, but it's a really clever way of doing it. Like, we just need a buffer of 16 characters, and that covers all of our bases in order to be able to do this. So we just need 16 bytes of memory to be able to print any integer that we want. Really cool. Okay, so then we just use this same function that we've been using to print other values, right? So if we're just printing like any value that is not a percentage symbol, we're just using that same one and we're printing whatever character was in our buffer here. All right, so that is how it works for decimals. How would it work for hexadecimal numbers? As it turns out, exactly the same. Amazingly, this works the same for hexadecimal numbers. Just any place that we were dividing by 10 and using modulo 10, we would use modulo 16. It works. It ends up working. It's really incredible. Yeah, really, really cool stuff if you ask me. And then, so then we have the pointer. It's a very similar idea. So let's go to this this function here. What we do is we just print first 0x, so it kind of gets a clear special value that it's a pointer, and then we end up doing a slightly different algorithm in order to print this to the screen. So let's go through this algorithm as well because it's also really interesting. So let's imagine we got a pointer and it's an address. Remember, a pointer is an address, and pointers in xv6 are 64 bits. So they're 8 bytes long. So let's do like, imagine our pointer was 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, A, B, D, E, F, 0. Is that right? That is 16 characters long. Yeah, so that is a 64-bit pointer. So yeah, what we're actually doing here is we're then going to iterate through our value here. So we've passed in our 64-bit number, so something like this, as x. And then while I equals 0, I is less than the size of a uint64 multiplied by 2. Well, the size of a uint64 is 8, and then multiplied by 2 is 16. So while I is less than 16, do two things. Increment I and take x and shift it up by 4 bits. So that's kind of a weird one, but let's go through the algorithm first. So the first time around, we're going to come into this function and we're going to use the same digits array, and we're indexing by this expression, which is kind of scary, but let's take a look at it. So x, this is our value, this is x. What we're doing is we're shifting x down by this expression. So what does this expression end up equaling? Well, size of uint64, we already know that that's 8, multiplied by 8, well that's 64, minus 4, so 60. So we take x and we shift it down by 60. So what would happen if we did that? Well, basically, that would end up shifting down 60 bits. Each hexadecimal character, you will recall, is 4 binary bits, right? So we're basically shifting from here down 60 bits. So what that's going to do is it's going to take the thing that's here and put it down here. It's going to end up equaling 1, right? We're shifting this down by 60 bits, so it's going to be 1. In fact, of course, it's going to look like this, because as you shift something down, you're actually shifting in kind of a 0 on the left-hand side, and you're pushing all of the bits that were shifted down kind of like out into the void here. So this kind of like, this is like, you know, Neverland. We don't end up here. Like, this is reality, and this is where all of those bits ended up. They got pushed out. So we end up with this value, which is just 1. And then we use 1 to index into the digits array. And of course, 1 is going to translate to the digit 1. So what's that going to look like? We're going to print 1. Then what we do is we increment I, and we shift x to the left by 4 bits. So what's that doing? Before, like when we're getting this index here, we're shifting to the right, which means we're pushing numbers down to the right. When we shift to the left, well, what are we doing there? We're taking this number, shifting it by 4 bits. Remember, each of these hexadecimal numbers is 4 bits. So we're shifting this one out. This goes off into the ether. There's nowhere for it. And we shift in a 0 on this side. So then we've got this is our new number. This is our new x. Right? X shift up equals, we're doing a shift up and reassign to x. And so now we're going to do the same thing again. And of course, we know what happens here. When we shift down by 60 bits, we end up with the value 2, right? So then we'll end up printing 2. And that's just going to continue for this entire number. Yeah, it's a really beautiful algorithm. That's going to end up printing out this pointer in order. And again, this is just one of the ways that you could do this. We could apply this same algorithm just to printing hexadecimal numbers in the same way that we saw it before. Only that before we were printing 32-bit integers here, even if they were 16-bit, sorry, base 16. In this case, they're set up to be 64-bit, so we're using like size of 64. The reason that we don't have some special function, or we don't reuse this function here to print hexadecimal numbers, is because this same algorithm that works for decimal numbers works for hexadecimal numbers. And all of this complication, a lot of this comes from the fact that we're trying to print decimal numbers, and decimal numbers and computers, they don't play well together. What you can see is that hexadecimal numbers and computers, they play really well together. And we can have really concise algorithms that just mess with the bits, and then we can actually get the same kind of results. Yeah, I think that's incredible. So that is the print pointer. Printing a string is actually really straightforward. What we end up doing is just making sure that the string is not 0 that we're trying to print. If it is 0, as in it's pointing to nothing, we actually set the whole string to be this string null. Then we print it. We just go character by character and we print it to the screen, and then we break. So that's it. That is the entire logic of this thing. And the only kind of thing left to talk about, which is not really even a big point here, but I think it's worth just making sure we touch on it, is that when we actually go to extract these arguments, what we're doing is we are grabbing like this value. We're actually doing that by calling this varg, variadic arg. We end up passing in the argument pointer. So that's kind of like we set it up. We said that, okay, we're going to start grabbing arguments after this format. So this format here, like after that, that's going to be where we grab arguments from. And at each moment, you have to specify what the type of the argument is that you're grabbing, because that information doesn't exist, right? We have to provide that every time. That's why things can go wrong in Printf. So in this case, we're printing out an integer, just a regular old integer. So we pass in the type int here, and under the hood, this varg, it ends up figuring out that means that it needs to find like 4 bytes, right? It needs to go and find a 4-byte value that's the next thing in the list and use that. And of course down here, when we go to print something that's hexadecimal, we do the same. And here, when we print a pointer, we pass in uint64. But it's all the same. We use this varg. And then every time varg is called, it ends up like moving the argument pointer forward as well. So each time you ask for a variadic argument, you're going to get the next one in the list. Incremented kind of by whatever the size of this happens to be, and also a character pointer here, which also happens to be 8 bytes. Okay, that is the entire workings of Printf. I think it's really fascinating. I think this is really interesting, and if you're hacking away on this, like you want to hack away, an interesting thing to do is to come into this printf function and extend it so that you can print stuff like 64-bit integers. Or 8-bit integers, right? So like specifically printing like certain types. So what you would do is you would kind of figure out what they're meant to be called in like the standard printf like notation. So like if you want to print a long integer, for instance, you use like L instead of D, and then you can go in there and kind of elaborate on this. I think it would be really fun. Like it's a fun way of doing it. So take a look into that if you're looking for kind of a project. Yeah, so at this point, we actually fully understand how printf works. So we've gotten to the point, right, where we've done all of these things. And in the next episode, we'll actually be looking into the page allocator. So I'm really excited about that too. Let me know in the comments if you've enjoyed this video. Let me know if the level of detail is too much or too little or just right. You know, it really helps me to see what I'm doing and make the next episodes interesting for people. Likewise, if something wasn't clear, let me know in the comments. I'll try to clear it up. Maybe in the comment, maybe in a future episode. But yeah, so thanks for watching, and looking forward to joining you in the next one for the physical page allocator.